Let's look at 2.6 related rates, some of selected homework problems. Uh, so we're looking at some volume and surface area problems. So for 14, a spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon increasing at the instant when the radius is 30 centimeters and part B 60 centimeters? So let's see, we know we're dealing with volume of a sphere. So we start off, go ahead and list out some information that we can gather from the problem. We know that we're dealing with the volume formula of 4/3 pi r cubed. Let's see, looking at some context clues here, let's see what else we can gather from this problem. The balloon is being inflated, so we know the volume is going to be increasing over time at a rate of 800 cubic centimeters per minute. So a couple of things here. We see the word rate, and we see this description, centimeters per cubic centimeters per minute. So we know cubic centimeters is a unit of measure for volume. Per minute, that's a rate, and also that's confirmed by this word rate here. So we know 800 represents the rate of change of volume. Okay, and it's increasing over time since this balloon is being inflated. So we know dV/dt, or the rate of change of volume with respect to time, is positive 800 cubic centimeters per minute. Okay, how fast is the radius of the balloon increasing? So how fast, that's a description that represents rate. Increasing, balloon is increasing, so is radius of the balloon increasing. We know that this is asking for the rate of change of radius with respect to time, so we know we're looking for dr/dt. Okay. Part A, at the moment when the radius of the sphere is 30 centimeters. So part A, we know that information as well. So we're given dV/dt, we're trying to find dr/dt, and also we have radius, and the equation we're working with is 4/3 pi r cubed. So we know we have to work our way down to the derivative in order to plug in and find our missing variable. So 4/3 pi r cubed, we're going to find the derivative of each variable with respect to time. So with the related rates, our independent variable is time. So each time we find the derivative, we have to attach a d/dt for that variable. So v becomes 1. This is v to the first power, so v becomes 1, but because we're involving v's derivative, we have dV/dt. 4/3 pi is the coefficient, so that's just going to stay out in front, and then really just have to worry about r cubed. The derivative for r cubed is 3r squared, and then because we're involving r's derivative, we attach dr/dt. So after we clean up the right side of this derivative equation, the 3's cancel out. We're left with 4 pi r squared dr/dt. So now we should have enough information where we can plug in and find the missing variable. We're trying to find dr/dt. That's what we're after. dV/dt gets replaced with 800. R gets replaced with 30. And then let's see if we can solve for dr/dt. So 800 replaces dV/dt. 30 replaces r, and then dr/dt is what we're looking for, is the variable that we're trying to solve for. So looks like the only variable that we have left is dr/dt. We're going to go ahead and try to isolate that. So we divide both sides by the 4 pi 30 squared. So when we do that, we get 800 divided by 3600 pi, and then that reduces down to 2/9 pi. We know that the radius is increasing, so we expect that to be a positive number, which it is. And we're asking for the rate, so centimeters per minute. It's a one-dimensional unit, so dr/dt is just going to be centimeters per minute, and the value being 2/9 pi. Okay. Part B, same everything. The only difference is now we're dealing with a radius of 60. So dr/dt is still the variable we're trying to solve for. dV/dt is still 800. Just have to replace r with 60 and isolate dr/dt by dividing the the 4 pi 60 squared over to the left side, and we get 14,400 pi. 800 divided by that value is our drdt, which reduces to be 1 over 18 pi centimeters per minute. Okay, next problem we're looking at is 16. This deals with surface area. All edges of a cube are expanding at a rate of 6 centimeters per second. How fast is the surface area changing when each edge is part A 2 centimeters and part B 10 centimeters? So we're dealing with surface area of a cube. So we know a cube has 6 sides, and each side has an area of x squared, or length squared. If we have 6 faces for a cube, and each face has an area of x squared, if we add them all together, we're going to get 6x squared. So that's the surface area of our cube. So that's our starting point. How fast is the surface area changing? So we know we're looking for the rate of change of surface area with respect to time. So dSdt is what we're looking for. When the edge, or the length of each side, is 2 centimeters, so x equals 2 centimeters. And we're told that the edges are expanding at a rate of 6 centimeters per second. So we know dx dt is going to be positive 6 centimeters per second. Again, we see some descriptive words to help us decide between positive or negative rates, right? If we see decreasing or shrinking, we know that's going to be a negative rate. But if we see expanding, or any value that tells us is increasing or getting larger, we know we're going to be using a positive rate. So let's go ahead and find the derivative. We have s being representing the surface area, s equals 6x squared. We find the derivative with respect to time. So s becomes ds dt. 6x squared becomes 12x dx dt. So we can go ahead and make our substitutions. We know dx dt is positive 6. Okay. We know x is 2, so we can just solve for ds dt. So ds dt is just going to be 12 times 2 times dx dt, which simplifies down to 12 times 2 times 6, which is 144 square centimeters per second. So ds dt. Okay, so surface area has a unit of measure of square centimeters, and this is talking about a rate, so per second. Part B, we're trying to find ds dt when x equals 10. So virtually the same steps as part A. We're just replacing x with 10 instead of 2. So go ahead and replace dx dt with positive 6, replace x with 10, and then we just solve for ds dt. So 12 times 10 times 6 is 720. Again, it's increasing because the length is increasing. We expect the surface area to also be increasing, so 720 square centimeters per second. Okay, number 20, we're dealing with a volume of a trough. So a trough is 12 feet long, 3 feet across the top. If the ends are isosceles triangles with an altitude of 3 feet, how fast is the water level rising when the depth of the water is 1 foot? Okay, so let's see if we can figure out what the volume formula of this trough is. So we know volume for this diagram is going to be 1/2 length times base times height. Okay. So it's a triangular prism here. So we can just basically think of it as the area of this triangle times the length or the height of this. If we can consider the triangle as a base, then the height is going to be this 12. Okay, so our volume formula is just going to be 1/2 of base times height, okay, times 12. Okay, and we're told that the base and height are the same. Is 3 feet across the top, and altitude of also 3 feet. So 1/2 base times height, they're both going to be 3. So we can say 1/2 times 6, so 1/2 times 12, which is 6. And since base and height are the same, we can narrow down our equation just in terms of height, since eventually we're trying to solve for height. So, or the information that's given to us is in terms of height. So because we know base is the same as height, we can replace b with h. We get v is equal to 6 times h, which is 6h squared. So here we have our volume formula for our triangular prism. So volume is 6h squared. We know the water is being pumped into the trough at 2 cubic feet per minute. So we know this is dealing with volume, and this is a rate. So we know we're dealing with dV/dt. So dV/dt, the volume is going to be increasing because water is being pumped into that this trough. So positive 2 cubic feet per minute. Okay. Find dH/dt when h is equal to 1. So we can go ahead and find the derivative. So v becomes dV/dt. 6h squared becomes 12h. We're involving h's derivative, so we attach a dH/dt. So let's go ahead and make our substitutions. dV/dt gets replaced with 2, h gets replaced with 1, and then our missing variable is solving for dH/dt. Okay, so 2 is equal to 12 times 1 times dH/dt. Divide both sides by 12. 2 divided by 12 is 1/6. So our dH/dt, or the rate of change of the height of the trough, is 1/6 feet per minute. Part B, water is rising at a rate of 3/8 inches per minute when h equals 2. Determine the rate at which water is pumped into the trough. So water is rising at a rate of 3 inches per minute. We see inches per minute. That's a one-dimensional unit. So we know that is referring to dH/dt. So we're given dH/dt, but everything we want is going to be in terms of feet per minute. So we want to have to convert the 3/8 inches per minute. So 3/8 inches per minute, because we know the conversion between inch and feet is 1 foot for every 12 inch. If I put 12 inch in the denominator and get the units to cancel out, and 3/8 times 1/12 is 1/32. So we know dH/dt after conversion is 1/32 feet per minute. Determine the rate at which water is pumped into the trough. So rate of water, this is a volume, so we're looking for dV/dt when h is 2. So we can go ahead and make our substitutions. dH/dt is 1/32, h is 2, and then we can go ahead and just solve for dV/dt. 12 times 2 is 24. 24 divided by 32, reduced to be 3/4. We're dealing with the rate of change of volume. So this is going to be cubic feet, but it's also a rate, so cubic feet per minute.